So the most famous theorem about uniform dimensional results is Kaufman's theorem about the Brownian motion from 1969. So let us consider a d-dimensional Brownian motion where d is at least 2. Then almost surely the dimension of the image of any A will be doubled. So on the dimension, I always mean the Hausdorff dimension all along. And it's called uniform dimensional result because it happens for all A at the same time. So it only happens, of course, in dimensions at least 2, because in one dimension, for example, all level sets have Hausdorff dimension 1/2. So then the image of a 1/2 dimensional set can be 0 dimensional or a point. So here, the valid question: what happens in dimension 1? So whether there is a similar theorem in dimension 1. So the answer is no. So for later comparison, let us we know the following. For a continuous function, and any d between 0 and 1, let IFD be we consider the image the dimension of an image FA for any d-dimensional set A. And we consider the infimum, so the worst possible case. And ID is we consider functions when it's maximus. So we take the supremum of these for all possible, let's say, continuous functions. So it is a theorem of András-Máté that for all D, for all F, these IF, D is at most D. So there is always the D-dimensional compact set C such that the image FC has dimension at most D. So it is, of course, equation because it's an equation, the ID will be D. So that is D. So this implies that ID equals D. So can I write here as well?
Yes, if you click on the cursor in the bar, the cursor, ahogy hányomsz, nyílt, fönt.
Tanító balra kettőben. Tanító.
Igen.
Balra, az.
Igen, és akkor most tudod fölfele nyomni.
Kézem.
Oh, that's practical.
És akkor most még visszanézve tovább, vissza kell klikkelni a volna, ugye? Igen.
Yeah, so this is of course just one direction, but the other is trivial. So I, D bigger than equal to D is shown by just the identity function. So this is seemingly a very innocuous result, but actually it answers a long-standing open problem of David Price and Benjamin Weiss. So this is here of Anderson as well, claiming that Hausdorff measure spaces of different dimensions. So this means that the measure spaces are the Borel sigma algebra and HS. This is smaller than T. So they are not Borel isomorphic. Oh, I don't even need a cursor. Oh, okay. So this is a very easy proof. After that theorem, so let us choose a D between S and T, and let F be a Borel bijection from R to R. Then from the above theorem of Mate, or a more precise version, there exists a compact set C. such that the dimension of FC is at most D, which equals the dimension of C. So now clearly we have that the S-dimensional Hausdorff dimension of C is just infinite, while the T-dimensional Hausdorff dimension of FC, so because D is smaller than T, is just 0. So now our main question is what happens. Oh, maybe this is useful as well. So what happens for graphs instead of images? So Keleti Tamás asked the question of the maybe the following, or at least the following flavor. So whether there exists a function such that its graph has maximal Hausdorff dimensions. So the dimension of the graph of F restricted to A is maximal 2 for each set A such that A has positive measure or a stronger version is a Hausdorff dimension 1. So having this in mind, so the answer will be yes, there exists such a function. But instead, I will consider for a function f and d the smallest possible graph dimension which f can have over a set of Hausdorff dimension d. So let's take the infimum of the dimension of the graph of f restricted to A, such that A has a given Hausdorff dimension d. And we want to maximize this. So we are looking for functions which has as large as possible graph dimension over any set A of given dimension d. So GD is just the supremum of these quantities for all possible functions. Yeah, so we have a trivial upper and lower bounds. Of course, GD is at least D, and at most D plus 1. How much time do I have?
So usually it's 55 minutes and seems
Yeah.
to be delayed by 15 minutes at least. So I think you can talk until 20, so 11:20.
Oh, that's a lot of time. Yeah. Thank you. So now I will give a better upper and lower bounds, but unfortunately they will not match. So that will be the question: what is the right exact evaluation for GD? Yeah. So for the lower bound, we will actually use fractional Brownian motions. Just big definition. So B is a fractional Brownian motion of first parameter alpha. So this is strictly between 0 and 1. If so, there are 3 properties, so everything is similar to the standard Brownian motion, which is the case alpha equals 1/2. So B is a Gaussian process. With stationary increments. Starts at 0 and T minus alpha times BT as standard normal distribution. And we have to assume that almost surely the function BT is continuous. So we can prove the following: let B be a fractional Brownian motion. With first parameter alpha then with probability 1, is quantity GBD equals 1 over alpha times D minus 1 minus alpha squared. So I will probably say a few words about the proof of the lower bound, which is the more interesting for us because it gives a lower bound for the quantity GD as well. So as a corollary, we get a lower bound for GD. So of course, then it's bigger than equal to the maximum of these over all possible values of alpha. And this takes the maximum at alpha equals square root 1 minus d, and it gives 2 minus 2 times square root 1 minus d. So this is actually the best lower bound, you know, and of course this implies that the limit of GD is at least 2 when d tends to 1. So GD tends to 2 if d tends to 1. So at the limit, at least, this is optimal. So this was the lower bound. And the upper bound, we know will be GD is at most d times 1 plus d. So this will actually follow from a theorem of HUN-REN. Stating if you have a Borel set and a Borel function on it, then for all s between 0 and 1, there exists a Borel set B A such that the dimension of B is S times the dimension of A, and the dimension of the image of B is at most S times the dimension of the whole image. So the proof of the upper bound based on this is fairly easy. So we consider GFD, and there will be two cases. The first case is when the dimension of the graph of F is big. So the dimension of the graph of S is bigger than 1 plus D. It means
Is it the graph over A or?
yeah, sorry, I just missed this. No, that's a whole graph. This is
The whole graph.
So this is a whole graph.
If you could show the result as well that you were showing.
So if the whole graph has large dimension, then there are a lot of line sections which can intersect the graph in a dimension bigger than D. So there is a line L such that the dimension of the graph intersected with L is bigger than D.
You were saying that it's non-vertical.
No, vertical, yeah, of course. But in almost every direction, there are positively many such lines. So this is a intersection theorem of maybe or oh. There is a function, there is a line with the intersection dimension bigger than D. So then we can just project the intersection and choose a subset with dimension exactly D, and over this subset, the graph will have dimension D as well because it is on a line. So that means there is an A such that the dimension of A is D, which is the same as the dimension of the graph restricted to A. So this just means that in this case, GFD is just the minimal D. So the second case is when the dimension of the graph is at most 1 plus D. Then using the above theorem of Martel, so the theorem will be used for the graph function which maps x to x fx. So the theorem then literally gives that there is a set A such that in A equals D, and the dimension of the graph of f restricted to A. So this is the graph f restricted to A. This is the image of A under this graph map. And it's at most D times the dimension of the whole graph, which is 1 plus. Summarizing the two cases, we get that GD is at most E times 1 plus. So putting together the lower and upper bounds, so this is the upper bound, and this is the lower bound. For example, for B equals 1/2, this gives that this is at most 3/4 and larger than or equal to 2 minus square root 2. Well, we conjecture that probably the lower bound is equality, but we cannot prove it. So this is the open question or problem. We want to determine GD. Okay, if I still have some, I still have at least 10 minutes, maybe more than that. It will be enough, I guess, then.
Yeah.
I'm waiting to see. So I wanted to say something about this Brownian motion. So we have the fractional Brownian motion. and almost surely for all set A with dimension D, we have that the dimension of the graph of B restricted to A is at least is 1 over alpha times E minus 1 minus alpha squared. And the sketch of the proof is based on a nice property of the fractional Brownian motion. So in probability 1, the following happens for the fractional Brownian motion. If we choose an interval of size 2 minus n, then of course we know that over the interval the oscillation will be around 2 to the minus n times alpha, right? But let us consider small subintervals of this. So with the size of, say, 2 to the minus k, then all of these subintervals will have an image here about the size of 2 to the minus k times alpha. So let's take all the subintervals here in the image, the dyadic ones with this size. So if we consider the images of all of these, they are basically uniformly distributed over these smaller subintervals of 2 to the minus n alpha of size 2 to the minus k alpha. Which means that the number of small intervals here of this size, no, not this size, but matching basically this dyadic interval is with a logarithmic error term, the same as can be calculated from here. We calculate how many intervals we have here, how many intervals of this size we have here in the bigger one, and we just divide the two. So basically, it's really uniform. So sometimes it's just easier to think about the Brownian motion as a self-affine function with the following pattern. We divide 0, 1 into 9 equal pieces, 1 over 9. and we consider this pattern. So here, the distribution of the small intervals are just uniform everywhere, and for a lot of considerations, this behaves the same way as the standard Brownian motion. So we can say that this is Lipschitz 1/2 as well, because it maps an interval of size 1/9 to 1/3, and it continues because we just iterate this pattern.
Further one.
Yeah.
Further 1/2. What did I say? Oh, yeah, further. So how can we prove a lower bound, which is in general the harder one to prove? We consider a covering. Oh, so here is a set A. We consider the graph over A, and we just take an efficient covering. So let's say the Hausdorff dimension of the graph is smaller than S, then it means that there are dyadic cubes of size 2 to the minus ni such that this parameter or I is small to the 2 to the minus ni times S. And based that there is a good covering for the graph, we will construct a good enough covering for A, which cannot be small because A has dimension D, so this S cannot be small as well. So that's the logic of the proof. So I will just sketch how the calculation here works. So we will use only this uniform distribution stuff here. So we have an interval of 2 to the minus n I. Here is r cubed or r squared. But we know that this interval has a much larger image. So here, the oscillation over this interval is of the size 2 to the minus n I times alpha. And if we want to match this size, we have to choose a small subintervals of the size 2 to the minus ni over alpha. So in order to get this one, so this k will be ni over alpha. And we have to just count how many of these small dyadic intervals match, are mapped exactly into the square, or just intersecting it. That's the same, basically. So let's calculate how many. So here we have to divide by 2 to the minus ni over 2 to the minus ni times alpha. So this is the division coming from the ratio of this is 1 over the number of intervals here of this size, and this has to multiply by the number of subintervals of this size here. So this gets 2 to the minus ni over 2 to the minus ni over alpha. So the number of these intervals is 2 to the minus ni times 2 minus alpha minus 1 over alpha. So this was the hard part, calculating this one. Basically, the rest is just really easy, because this gets that this is the number of if we have a scale covering the graph of the size 2 to the minus ni, then for A it gives these many intervals of size 2 to the minus ni over alpha. So for a Hausdorff dimension calculation, if we want A to be of small dimension, let it be ni. It is enough that this sum ni times 2 to the minus ni over alpha times t is smaller than epsilon. In order to get this, we have to compare this let's make it equal to 2 to the minus ni times s, which gives an exact formula for t. So this gives that s equals 2 minus alpha minus 1 minus alpha plus t over alpha. So if this is the relation between s and t, then we will get simply that the dimension of A is at most t. But we know that this is at least d. So we want to get an efficient covering on the graph or the image, and we just pull it back to the original interval. And if there would be a too great covering of the image or the graph, then it would conclude that it's just too good for the original interval of cells. And this is actually a nice and useful argument, I guess, in a more general context. So thank you very much. This is all, I guess. Thank you.
Yeah, thank you very much. Questions? Maybe I have. So the GFD is to take the infimum. So what which one do you believe? The lower bound you believe that this is optimal?
Yeah, at the moment, I guess.
I see. So you then really have to estimate every function. So the GP is taking infimum path or taking the supreme path.
The GD is supreme, so GFD encodes that all graphs over any set of Hausdorff dimension G is at least GFD, and we want to maximize it. So we want to look for a function for which is as large as can be over all set of dimension D at the same time. So that's what uniform means basically.
So and did you get this or similar estimate if you, instead of the Brownian notion, we use exactly that self-affine?
We get the same metrics, but this sounds better, and of course for self-affine function we, at least in this simple form, it only exists for a countable dense subset of 0, 1, but basically that's the same, same argument.
Further questions?
Is there some reason why you think this fractional Brownian motion is basically this optimal function?
Yeah, because of this uniform distribution of intervals. So there is one free parameter, the Hölder exponent, that how much an oscillation will be over an interval, and between that it's just uniform. And I mean, at least I cannot come up with a better example, but who knows, maybe there is one.
The other reason is that this is, and the other estimates are quite ad hoc estimates, and this seems to be, I mean, this is very suited.
The other estimate is sharp in that form, but here we have another restriction that it is applied to a graph of a function, which is not really used in that argument. So that is definitely a gap there. So that's another reason why the lower bound can be optimal, but maybe not all of them is not.